numbers and operations. So when we say operations, we're talking about like addition, subtraction, multiplication, division, etc. And really the thing about expressions is that they really just represent single values. So when we did arithmetic and we had a problem like 4 plus 5, we're like, oh, that is equal to just the number 9, right? So it has a single numerical value. Well, I might not know what the number x is, but if I add 5 to it, that entire expression also has a single numerical value. I can't write it as a single number because I don't know what x is, but it behaves just like the 9. I can do anything I want to it to create another number. So anytime you see an expression, that whole thing has a single value. So it's just one number. We just can't actually do those calculations, so it's not quite as pretty as when we get to just write the number 9. When we find the value of that expression for a specific value of x, that's what we call evaluating an expression. So finding the value of an expression for a specific value of the variable. Or variables if there's more than one. So we're plugging numbers in. The most important thing about evaluating expressions is to put parentheses around your replacement values. So replacement values so the number that you replace your variable with should always be in parentheses. It is true that sometimes you can do it without parentheses and it doesn't affect the answer, but I always think it's better to have them and not need them than not have them and need them. So as a general rule, I always put the number in parentheses, and then if I find I don't need it later on, I can just drop the parentheses. So let's do a couple of these. I don't like that one. Let's do that one. So as far as what you're showing me when you do this, I'm pretty confident you guys all know how to do calculations, and you have a calculator to do it anyway. So I'm not too worried about you showing me how you multiplied two numbers or how you added two numbers. What I want to see is the first step, which is where you replace the variables with the numbers without changing anything in the expression. And then I have to see the last step, of course, which is your final answer. So for these specific problems, like on a test, I usually grade them out of 2 points, right? So like the first step is to replace x with -3 in parentheses and replace y with -6 in parentheses. Notice I didn't try to do any calculations in that first step. We're just rewriting the expression exactly as written, but with numbers instead of variables. And so that would, like on a test, that's 1 point. And then the second point would be your final answer. In this case, I'm going to like do the calculations just because I don't have my calculator handy. What should I do first?
Square both numbers.
Yeah, we're going to square -3, which is 9. And then we're going to square -6, which is 36. Notice that that subtraction stays the same, right? Because we do exponents before subtraction. It can be tempting to do this. I know that's what I learned like when I first learned about positives and negatives. And like it really got stuck in our heads that like if you have two negatives, you get to just make a positive. But unfortunately, we learned that before we were introduced to exponents. And so once exponents come into play, we can't just make two negatives a positive. So it's all about order of operations. Remember that we always evaluate exponents before we perform subtraction. So if we were to do that negative, make the negative and the negative into a positive, that would be doing the subtraction first, or using that subtraction first. So that's why we square this -6 first, and then we get, what is it, like negative 27? Right? Yeah. Make sense? Mm-hmm. So if you were to plug that whole thing after that first step into your calculator, honestly, like, I really don't care, and then spit out -27, as long as you're plugging it in correctly. Using a calculator is a skill, too, that you'll need. Questions so far?
So you always put parentheses around the number, or like the letter?
Yeah. And one way, if you find yourself getting tripped up about like where like negative signs in particular should go, like is where most people get mixed up, you can always write it with the variables and then like put the parentheses in, and then just like take your eraser, because you guys are all going to use pencil, and put that -3 there. And that way, if there's random negative signs like in the original expression, you're not like affecting what operations are in the original expression when you put that number in. Make sense? I feel like I can't write it and not do it. Okay. And again, make sure that you're showing at least that first step. So one thing you'll notice is that algebra is really all about the process. So that's what we're focused on, is how we get there, not what we get at the end. Okay, why don't you guys try that one? So remember to write down that first step and then follow order of operations. 5 times 2. What should we do first? Mm-hmm. What operation did we just do? Like in order of operations? Multiplication, right? It's tempting to like see those parentheses and think you're doing like the parentheses step, right? But remember, parentheses, that step really means do operations inside the parentheses. Here we just have numbers inside the parentheses. So those parentheses aren't grouping any operations. So those parentheses don't tell us that we have to do 5 times 2 and 4 times -10 first. That's multiplication, right? So we do multiplication and division from left to right. What's my next step? Yeah, to do that division. So we get -8 times 2 is -16. And if the whole left to right thing is troublesome for you and you want just like a set order that you do it in, you can always do division first and then multiplication, and you'll get the correct answer. You just can't do it the other way around. So if I did -10 divided by 5 here first, I would get 4 times -2 times 2, and then do all that multiplication, and you get -16. So if it's simpler for you to do the same order every single time, then it's division, then multiplication. The same is true of addition and subtraction. You can always do subtraction first and then addition, but you can't do it the other way around, which begs the question why the acronym is the acronym that everybody teaches. But we won't get into that today. Any questions on that one? That one's a little tricky just because it's really tempting to do 2 things at once, which causes you to go out of order. Okay. You guys feel good about evaluating expressions? You happy to move on? Okay. So we're also going to solve linear equations in one variable. Again, this is likely review, I hope. We want to talk first about how many solutions a linear equation can have. So it can have one solution, which is what we usually think of when we think about solving an equation. So if I have something like x plus 4 equals 9, I'll subtract 4 from both sides. So subtracting 4 from the left side gives me x, subtracting 4 from the right side gives me 5, and my single solution is x equals 5. That means if I replace x with 5, it'll make my equation true, and there's only one number that'll make that happen. There's a couple other possibilities. One is that there are no solutions. So what happens here is, let's see, the simplest case is something like x equals x plus 1. So if we think of this equation just in terms of what it says as opposed to like how we're going to solve it, what it says is that a number is equal to 1 more than itself, right? So 3 equals 4, or 5 equals 6, or 7 equals 8, right? Which is impossible. Like a number can never be equal to 1 more than itself. And we call that a contradiction. Ooh. I'm sorry, that's from last semester. So contradictions are equations that are never true. And they're not always this simple where you can just look at them and tell that it's a contradiction. And so you can go through the same steps to solve the equation as you would any other equation. So I'd be like, oh, I need to get all terms containing x on one side, so I'll subtract x from both sides. What do I get on the left side if I subtract x?
1.
How about the other left side? 0, good. Right, x minus x is 0. X plus 1 minus x is 1. And is 0 equal to 1? We get a statement that's never true, right? And that tells us that there is no solution. Be sure that you actually make that conclusion at the end, right? So don't stop here. You actually want to say, okay, this means that there's no solution to that equation, which means no matter what number I plug in for x, this equation will never, ever be true. And then the last possibility is that there are infinitely many solutions. Many solutions. And we actually see equations like this all the time in the form of like formulas and rules, you know, like the things in your textbook that are in like a shaded box. Like, for instance, the distributive property. It's an equation that's always true no matter what numbers we plug in, right? So you might get an equation like this. And again, this is kind of a simple example that's somewhat obvious, but it's not always the case. And so you just follow the same steps you would to solve any equation. We'll distribute on the left side. And hopefully at this point you would realize that both sides are the same no matter what we put in for x. However, if you didn't, the next step would be to get all the terms containing x on one side. So I'd subtract 4x from both sides, which gives me 8 equals 8, which is what we call an identity, which just means it's an equation that is always true. 8 is always equal to 8. And so my solutions are all real numbers. And that just means I can pick any real number, plug it in for x, and the equation will be true. Notice that these last two situations, my x goes away both times. The difference is that when there's no solution, you get a statement that's never true, right? You get a number equal to some different number. Whereas if there's infinitely many solutions, you get a number is equal to itself. So you get a statement that is always true. And that's how you tell the difference when you're solving. And like with this last one, as soon as you can tell that it's an identity, you can just write all real numbers. Like, I don't necessarily expect you to go all the way to 8 equals 8. Like, if you can recognize it, that both sides are the same, that's fine. Any questions on those? Okay. So let's do this one. What do you guys want to do to solve this equation? Yeah, so you're thinking like we should get all the terms that contain x on one side, right? Which is definitely what we do first in every other equation. The only problem here is that there's fractions. And I don't know about you, but I find fractions to be kind of a pain. And so I like to just get rid of the fractions first. It's not how I learned to do it originally, but once I got the hang of it, I found that it's a lot simpler to clear fractions than to do a bunch of operations with fractions, like do all the adding and subtracting and dividing. So if I want to clear fractions, I'm just going to choose a number to multiply both sides of an equation by, which I'm allowed to do because this is an equation, and so I have a balance. I can multiply both sides by 10 billion if I feel like it, and it doesn't affect the balance of my equation as long as I'm doing it on both sides. So I'm going to pick a convenient number to multiply both sides by, which is the LCM of the denominators. The LCM is the least common multiple, which is the smallest number that all of the denominators divide into evenly. LCM and LCD are essentially the same thing. LCM is a property of numbers, LCD is a property of fractions, but they end up being the same number, so people usually use them interchangeably. So the LCM of my denominators is what? So 5, 10, and 4. 20, right? So I'm going to multiply both sides of this equation by 20. And it's 20 over 1, so the actual number 20, not 20 over 20 like we would do if we were getting common denominators. And if I'm multiplying the entire left side by 20, then I have to distribute it to both terms, right? So we'll do 20 over 1 times 2/5 x minus 20 times 1 equals 20 over 1 times 3/10 x plus 20 over 1 times 1/4. And then we'll go through and simplify all of these. You guys can use your calculators for this if you want to. Remember that you have them. It's okay to use them. But if you want to do it in your head, the simplest way is to divide your LCM by the denominator. So 20 divided by 5 gives me 4. So I have a factor of 4 on the top, times that factor of 2 that I already had gives me 8x. And then 20 times 1 is 20. 20 divided by 10 gives me a factor of 2 times 3x is 6x. And then 20 divided by 4 is 5. And I do it that way only because I know that 20 is divisible by all my denominators. So if this was just any old fraction that I was simplifying, I would do like prime factorization and cancel, because I don't know that the entire denominator will cancel in another situation. But here, I set it up so that I can divide that 20 by every single one of the denominators. And now we don't have any more fractions, so we can go ahead and get all terms containing an x on one side. So subtract 6x from both sides. And then we'll add 20 to both sides. And divide both sides by 2. And we'll leave our answer as a fraction. So when I first learned about improper fractions, I was given the impression that like they were super improper, which isn't actually the case. So the reason they're called improper fractions is because like in English, it's improper to say I have 25 halves feet of rope, right? That's improper English. It's not improper math. So the only time we will change that into a mixed number is if it's an application problem and we're writing a sentence. Like if I ask you how much rope, you would say 12.5 feet of rope because that makes more sense out loud or in a sentence. But mathematically, it's easier to work with fractions than with mixed numbers. In fact, we usually have to change mixed numbers back to fractions if we want to do any calculations with them. So we're just going to leave it like that. So simplified fraction, not a mixed number or decimal. Make sense? Any questions on this process? You guys, most of you seen it before, clearing fractions. Okay, let's do that one. So we're going to use the same process here. What should I multiply both sides by? I could, yeah, 30 would work. Like it wouldn't hurt. I just have bigger numbers all the way around. But my LCM is 15. And that brings up a good point. Like it's not wrong to multiply by anything. Like I said before, I could multiply both sides by 10 billion if I wanted to. And that's not incorrect. It just might not help me get where I'm trying to go. So if you did multiply both sides by 30, that would be totally fine. You would still get the same answer. So one thing to note on this one is that this entire thing is a single term, right? Like in the last problem, we had 2/5 times a variable. Remember how we talked about like x plus 10 is a single number, right? And so that negative 2/15 times x plus 10 is going to behave just like the 2/5 x. We're just going to multiply that by 15 once. We don't like distribute the 15 to both those terms. So we're going to do 15 over 1 times negative 2/15 times x plus 10. And the reason I know that that's all one term is that the outermost operation is multiplication. So terms are separated by addition and subtraction. And the only addition and subtraction in that piece of this equation is inside parentheses. And so it's not separating two terms. So now we have 15 times 1/3 x equals 15 times 1 plus 1, whoop, I missed one, 15 times 1/5 x. Okay, you guys simplify from there and solve away. Okay. So we simplified and got -2 times x plus 10 plus 5x equals 15 plus 3x, yeah? And distribute and combine like terms. Gave me 3x minus 20 equals 15 plus 3x. And so I'm already a little suspicious because like the variable term on both sides is the same, right? So if I subtract 3x from both sides, both my variable terms are going to go away. And what does that tell me? Yeah, that there's no solution. Excellent. Good. Okay. Last thing for today is we're going to solve what we call a literal equation. We're going to start with really simple ones. Now we'll just do a couple here and there, and then we'll do quite a bit more as we go through the semester. But when you solve a literal equation, all it really means is that you have an equation that has more than one variable in it, and you're solving for a specific variable. So the idea is to treat everything like a number except the variable you're solving for. So this equation is essentially the same as like 10 plus 6y equals 18. I mean, well, technically there's two numbers over here. Right, but the first thing we would do is multiply those. So the equation that I have on the left is essentially the same as that, right? It's a number plus a number times y equals another number. And I want to get y alone. So the process for doing that is exactly the same as it is when I have numbers. What would I do first over here on the right?
Subtract ax.
Yeah, we're going to subtract ax, right? Because over here we'd subtract 10 from both sides to get that 6y by itself. You want to think to yourself, I'm going to get all terms that contain my variable on one side. And so any other term gets moved to the other side. So we subtract ax from both sides, which gives me by equals c minus ax. And then how do I get y alone? Yeah, we'll divide by b. And because there aren't actually any calculations that I can do here, you don't have to worry about doing it like term by term. You just want to take the entire right side and divide it by b. And that's your answer. So these problems look a little bit more intimidating than like a regular equation just because there aren't a bunch of numbers in it. But if you find yourself getting tripped up on it, just throw numbers in for everything that isn't the variable you're solving for and just walk yourself through that process and do the same thing without the numbers. It works out just fine. Good? Okay, tonight you have, you're going to register for my math lab. You're going to read the syllabus. Definitely come with any questions that you have. If you finish your student info sheet, you can turn it in on your way out. If not, just turn it in tomorrow. And then you have one assignment in my math lab, so an online assignment, and then an assignment out of the book. Remember that you can use the e-text in the book to access that written work, so the problems out of your textbook. I'll be in my office from 1 to 3 if you have any questions or concerns. Have a great first day.